Hey guys, Dr. Tracy here, and this is a video to describe signed integers. Now I know this part gets a little confusing because it doesn't seem entirely intuitive, but when representing decimal integers, we have to have something that indicates whether or not they're negative or positive. So we get into signed integers. Now this presents a mess when trying to do addition or subtraction. So if you say represented a number like 2, binary would be 1, 0, that's positive 2. And if we added a bit to indicate that it's negative 1, 0, 1, 0, but then when you tried to add them, you're going to get a different number because 1, 1, 0, 0 in binary is actually equivalent to 12, not 0, like it's supposed to be. So the way that it's used within computers is something that's called the 2's complement code. And this is a way to represent signed decimal integers by using the opposite number. Now, I like this analogy because it says that pretend you have a cassette player or a VCR or whatever, and there's a counter that is the starting point at 0. If you go forward, that counter is going to add up, just like it would if you're counting to 1, 2, 3, 4. But if you go backwards and you start at 0, 0, then the first number it's going to get to is 9999 because it's going to move all those zeros back to 9. Now that's the way that the complement code works. The way it works is by taking the largest number possible and then going back one to show that that is the opposite. So in that case, if we have a binary, if we have a number that's listed in binary, if we use the 2's complement code, we don't need to worry about the carry because we can add them together to create a pattern for representing decimal integers that are negative. And you can see how this works out here. If we have 4 binary digits, we use the digit, the signed decimal with the 2-bit complement code. Now that's represented right here, where you can see 0 is represented in binary by 0, 0, 0, 0, pretty easy. And then just like rolling back the counter on a VCR or the mileage on a car in reverse, I guess, negative 1 becomes 1, 1, 1, 1. Negative 2, it's counting down now, 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 0, 1, 0. Anyway, as it counts down, those become representative of being negative numbers, whereas the positive numbers count up. This would be the same way that a counter might count down to 9998, 9997, etc. So the higher order bit of each positive number is 0, and each negative is 1. So the way that you can find the values of signed numbers to be able to tell if they are negative or positive is to create the numbers on either side representing the code, with the largest number being the largest possible negative number and the largest number on the other side being one slightly less to make it positive. And so in the 2's complement code, the negative of any n-bit integer is defined as x plus or minus x equals 2 to the n. So it's written as the same number as if it were the power, unless it's negative. So that the second n written in binary is 1 followed by however many zeros. So that requires those bits represent that. In the n-bit 2's complement code, adding a number to its negative produces n zeros and carry. So if we added negative 1, we added negative 1, which is 1, 1, 1, 1, to positive 1, which is 0, 0, 0, 1, then you'll see that each time we're adding, we would have a carry. But since the carry is disabled under signed decimals because we have negatives, 1 plus 1 is 0, carry the 1, 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 and the answer would be 0, which is what it's supposed to be. Negative 1 plus 1 equals 0. And the same is true with any of the other numbers. So this is the 2's complement. -4, this is 0, 1, 0, 0. And -4 is 1, 1, 0, 0. If we wanted to add those two together, then you would see that 0 plus 0 is 0, 0 plus 0 is 0, 1 plus 1 is 0, carry the 1, 1 plus 1 is 0, carry the 1, and no carry function. So -4 plus +4 is equal to 0. And that's how it is represented as the complement. So to find the complement of any integer and compute the 2's complement, you would take the complement of the x, just flipping all the bits, and add 1 to the result to make up for the fact that 0, 0, 0 use parts of the digits. I hope this was helpful to you. The exercises that come out of here are going to ask you to convert signed decimal integers to 2's complements. So that's where you're going to take the invert of them and add 1. And then develop an algorithm that will do that for you. And then the following 8-bit hexadecimal values are stored in 2's complement code. What are the equivalent signed decimal numbers? So you're just going to use hexadecimal to find the number and then determine the decimal number from the binary. And then the 16-bit are stored in 2's complement code. So you can assume that as 2's complement code, you're going to see which ones are negative and positive based on the values that are given. The answers are here, and when you give the answers, I don't want you to just repeat the answers to me. I want you to show me how you did it. So anyway, there you go.